Okay. Good morning, Moz. It is Wednesday morning, 8:20 a.m. I'm going to record problems number 4 and 5 from the week 3 study guide. All right. So I got it in the writing pad over here. We'll just share my screen and we'll get right to it. Okay. So here we go. This is problem number 4 from the week 3 study guide. Let's take a look. We have a thin. Okay. Thin now. If you're looking through the lecture notes, it's very important to understand the difference between thin and fully thick materials. When a material is thin, we can understand that it has plane stress assumptions, and that means something about reducing the 6x6 compliance and stiffness matrices down to 3x3 compliance and stiffness matrices. Okay, so a thin, very important, unidirectional ceramic matrix composite been fabricated with 40% silicon carbide fibers in a cast matrix. Okay, cast is a glass ceramic of calcium oxide, aluminum oxide, and silicon oxide, dioxide. Both constituents are isotropic. That's good to know. Cast has an elastic modulus of 87 GPa, Poisson's ratio 0.22. Silicon carbide has elastic modulus of 320 GPa and Poisson's ratio 0.18. All right, so we're going to figure out some things about the composite that gets made with these two different constituents. So let's get to it. First, estimate the composite properties, E1, E2, nu12, and G12 using Halpin psi equations. All right, we've done this quite a bit now, so let's just get right to it. I'll put the equations up here, and then I'll just give you the answers. But all right, E1 would use Halpin psi. Let's just remember what the Halpin psi equation is. Generally, property of the composite is equal to property of the matrix multiplied by 1 plus xi eta VF all over 1 minus eta VF. All right, that's Halpin psi equation. Used it a lot, but you would use different values of xi for different material properties, right? So if you're looking for E1, use the value xi equals infinity, which is rule of mixtures. Okay, same thing for nu12, you use xi equals infinity. Sorry, that's a bad infinity symbol, which again is rule of mixtures. If you're looking for G12, use xi equal to 1, and if you're looking for E2, you use xi equal to 2. All right, so this is Halpin psi, done it a ton. You can do these calculations. I'm not going to go through all the calculations here. I'll just jump to the good stuff and just give you the answer, just so you have it. If you want to work on this on your own, that's fine. Here, if you work through this yourself, you'll find that E1 is 203.5 GPa. E2 is going to be 168 GPa. We have G12 is going to be 65 GPa. And finally, nu12, which would also use rule of mixtures, is 0.2. All right. So this is all just part A of this problem. It's using Halpin psi. We've done a ton of Halpin psi already. I don't think it's all that useful to go through those calculations again. That should be pretty straight ahead. All right, so let's move on. Part B, we want to populate the in-plane compliance matrix in principal material coordinates. All right, so now remember your compliance matrix relates stress to strain. All right, so remember exactly what that is. That here the strain is equal to the compliance matrix times the stress matrix. Okay, that would be in the normal condition. This is 6 by 1, 6 by 6, 6 by 1. But if it's thin, we have plane stress. So if thin, then we still have the same form of the equation, but now this is all in plane stress. These are plane stress, right? So if thin now, these are different sizes. This is 3 by 1, this is 3 by 3, and this is 3 by 1, right? So it's asking us to populate this compliance matrix. So there's a couple of different ways to do this. I think the easiest way, since we have the material properties, is to just use the equations for compliance matrix given engineering properties straight away. So for plane stress, you can calculate the compliance matrix. This is in your equation sheet as well. as this is 1 on E1. This is negative nu 1, 2 on E1 and 0. Okay, negative nu 1, 2 on E1. This is 1 on E2. This is the 2, 2 entry, 0, 0, 0, 1 on G1, 2. All right, this is populating that guy. You have all of these, right? E1, nu 1, 2, E2, G1, 2. These are things that you calculated in part A, or you should have calculated in part A of the problem. They're all right up here. I don't think it's all that useful, again, to kind of go through and do all these calculations like manually at this point. So I think we'll just, cut to the answer and say, all right, if you go through all this, your compliance matrix should look like this. So these are the values. If you're actually to punch this in, this is what you would get. Units here are 1 on GPA. All right, so that's part B. Let's keep going with part C. Calculate the in-plane stiffness matrix in principal coordinates. This is Q. Again, a couple of different ways to do this, but you remember that the stiffness matrix is the inversion of the compliance matrix. All right, so if we want Q, this is the inversion of the plane stress compliance matrix. Okay, so if you'd like, just take this and invert it in MATLAB, right? Just take it to the -1 power in MATLAB. MATLAB can do that for you. Or there's another way that you can do this, and that is to calculate Q directly. So Q can also be calculated directly. So two ways here is just do the inversion in MATLAB, right? So just do MATLAB S inversion, and that'll get you your answer. All right. The second way is calculate Q directly. Okay. And if you want to do direct calculation, you can do it in the following way. This is from your equation sheet. I'm just going to copy and paste this information. So the direct calculation would be the following, where if you're trying to populate the Q matrix, it's Q11, Q12, 0, Q12, Q22, 0, 0, 0, Q66. This is what it looks like. And if you want to calculate them directly, this is how you would calculate it. Q11 is calculated as E1 over delta, where this is delta. All right, so delta is known. You see delta in the denominator of all these terms here. This is the value of delta, 1 minus nu 1, 2 squared times E2 over E1. All right, so you have all of these things. All of these things you know, again, from part A, so you can calculate Q directly just by punching them in and solving. All right. Alternatively, you can just invert this the compliance matrix to get the stiffness matrix. But if you do that, this should be what you end up with at the end. And this is in GPA. All right, so this is the answer for part C. Part D, let's take a look at that. Calculate the in-plane stiffness matrix of the composite in an XY coordinate system rotated 30 degrees from principal material coordinates. All right, so now we want to take our stiffness matrix and rotate it 30 degrees from principal material coordinates. All right, so we're looking for Q bar when the rotation angle is theta equals 30 degrees. So remember what that means. All right, you have a unidirectional composite. Here's your unidirectional composite, all the fibers running in one direction, right? So this is your traditional unidirectional composite, and your coordinate system would be one direction here, two direction here. One direction in the direction of the fibers, two direction across the fibers. So what the problem is asking you for is, all right, we know the stiffness matrix in the 1, 2 coordinate system. This is it right here. We want a stiffness matrix now, not in the 1, 2 coordinate system, but in a rotated coordinate system. A coordinate system that's rotated 30 degrees from this, and we're going to call that the XY coordinate system. So we need a new stiffness matrix in the XY coordinate system where this has been rotated 30 degrees from nominal. All right, well, that again is just a calculation that you can find in the lecture notes, in the equation sheet. It's just transforming Q from the current coordinate system to the new coordinate system. And so if you want to do that, you'll have Q in the new coordinate system. Let's call it the XYZ coordinate system. And here's the calculation for it. It's T inverse times Q in the 1, 2, 3 coordinate system times T star, where these are transformation matrices, right? So this is going to be a 3 by 3. This is a 3 by 3. These are all 3 by 3s. Okay. And, T and T star, they're calculated, using the angle theta. So for a thin laminate, this is what T is going to look like. Here's what T star is going to look like. Bring that in here. And M and N are just sine and cosine of the rotation angle theta. So this is, again, all in your equation sheet. So all these things are known. The rotation angle is 30 degrees, so you can calculate M and N. And then plug them in here, make all these 3 by 3 matrices using the M squared, N squared terms, etc., etc. Plug those in here, do matrix math using your 3 by 3 matrix Q, and you can come up with the 3 by 3 matrix in the rotated coordinate system. We'll call this Q bar, where theta equals 30 degrees, right? This is the rotation angle, theta equals 30. And if you punch that in, you'll get the following. Just started raining and my dog is freaking out. He really doesn't like thunder and lightning. Come here, buddy. Come here. Yeah, my dog's freaking out a little bit. But okay. So this is the stiffness matrix Q bar after the 30-degree rotation angle. So this is again in GPA. All right. Moving on, part E. Calculate the in-plane compliance matrix. Okay, again, this is just doing an inversion in MATLAB. Okay, so S bar is Q bar inverse. So again, MATLAB or Excel, whatever you want. And you can just calculate that straight away. I'm not gonna ask you to do an inversion by hand on the exam, okay? So just be aware of that, like just moving forward. So this is 1 on GPA. This is part E. Let's look at F. Determine the in-plane engineering property of the composite in the XY coordinate system. Okay, so this is just plucking values of the compliance matrix and transforming them into engineering constants. So remember that the compliance matrix in rotated coordinate systems looks something like the following. So S bar can be written in terms of engineering properties as this guy. Okay, so this is in terms of engineering properties, right? But we already have what S bar is. We know what it is in the rotated coordinate system. It looks like that. So if I want, let's say EX, well, I'll just pluck this guy and the first entry here and say that, all right, if I want to know the engineering properties, okay, I'll say, okay, 1 on EX is this guy, 0.0056516. So with just algebra, then EX is the inversion of this. Okay. So we can calculate that. 177 GPA. All right. You could do similar for, new X, Y. You could do similar for all the rest of these, right? So we see negative new X, Y on EX is equal to the 1, 2 entry of X. Okay, so the 1-2 entry of x is negative 0.0014568. One on GPA. Okay. We have EX, we know that from before, so 177. So the only unknown here is this. So you can solve for Poisson's ratio, which here in this case is going to be 0.258. Okay. You can do the same with the other parts of this. You'll find EY equal to 162. And you'll find GXY, or should find GXY, is equal to 74.2 GPA. Okay, so those are the 4 answers for part F. Lastly, G. After all that work, discuss why these predictive properties are likely not accurate, given what you know about ceramic materials when used in practice, and assumptions we make when predicting HALP and psi. How could you obtain more accurate material properties if you really wanted to know the true values? Okay, so let's take a look at part G. So after all this work, after all this stuff, let's talk about why this probably is not accurate. It's not accurate for a couple of reasons. First, let's discuss it just from a perspective of ceramic composites. All right, ceramic composites, what do we know about them? So ceramic fiber composites, right? They have poor bonding between fiber and matrix. Okay, and that's because ceramics are like inert by nature, right? It's difficult to bond ceramics to anything, right? So they generally just have poor bonding on the whole, right? So because of that, HALP and psi, which we use for part A, it's the basis for all of this, right? So in part A, we calculated E1, E2, G12, nu12, and so on and so on and so on, using HALP and psi equations. One of the underlying assumptions of HALP and psi is that there's a perfect bond between the fiber and matrix. Requires or assumes perfect bond between fiber and matrix. Which, we don't have here because it's a ceramic. All right. Okay. So that's it. That's problem number 4. I'm gonna try to move on here. My dog is really not having a good time right now. You can skip ahead if you need to for just a second. Come here, buddy. Come here, Rocky. This is my dog. This is Rocky. He's not enjoying himself because it's thundering outside right now. So um, he's having a bit of a hard time. But I'm gonna try to get through number 5, and then I'll take care of my dog. But okay, let's go. Let's do number 5. I'll bring it in here, and then we can go through the solution. Okay. A thin, high temperature unidirectional composite has the following properties. We'll go through this quickly. Populate the compliance matrix. Okay, well, we've seen that. We know what that looks like. This is from the equation sheet and the lecture notes. Okay, you have all these values, plug them in and just do it. All right, do the calculation. If you do the calculation, you should end up with the following compliance matrix. Okay, this is 1 on GPA as units. And this is the answer for part A. All right. For part B, stiffness matrix Q is the inversion of S. Okay, again, do this in MATLAB, Excel, whatever you want. But all right, no problem there. This is GPA. Okay, continuing on, part C, determine the off-axis in-plane compliance matrix for this material if loaded as shown 40 degrees off-axis. All right, so again, this is just a transformation. So C, we have the compliance matrix off-axis. So this is for theta, a rotation angle of 40 degrees. So in the last problem, we saw 30 degrees. This time we see 40 degrees. Here, this is going to require us to transform the compliance matrix. The last problem, we transformed the stiffness matrix. So just make sure that you have this correctly. But again, this comes from the equation sheet. It's T star inverse times S, which you have from part A, times T. All right. So this is generally the equation here. These are your rotational or transformation matrices that use M and N, right? So we know that based on the angle theta equals 40 degrees, you can populate T star, you can populate T, you know S from part A. Away you go. All right. Do all that. You can calculate S bar as the following. This is 1 on GPA. Okay. There you go. All right, part D. If the thin lamina is subject to biaxial loading with an off-axis angle of 40 degrees, determine the off-axis in-plane strains. Now we're getting to something new. So we have this compliance matrix S bar. We have some loading condition, which is some stress in the X direction of 20 MPa, some stress in the Y direction of 25 MPa, right? So what we're looking for is the strain in the XY coordinate system, which here is going to be strain in X, strain in Y, and gamma XY. It's a 3x1 matrix. And this is calculated according to compliance matrix S bar off axis multiplied by the stress in the off axis coordinate system. Okay, so this is our general setup. We have this from part C. It's this guy here. And now we just need to populate this. Well, we're given in the problem that we have biaxial loading. Sigma X is 20 MPa, sigma Y is 25 MPa. We're going to assume tau XY is 0. It says biaxial loading, so we can probably assume that to be true. And then away we go. So you have this, you have this, you can calculate this. Right? If you calculate this, you will get the following. (826 microstrain, 1,600 microstrain, and negative 2130. And this is all microstrain units. All right, so that's part D. It's loading off axis to understand what the strain is off axis. Calculate the shear coupling coefficients. You can do this with clever manipulation. All right. So remember what the full off-axis compliance matrix looks like? In terms of engineering properties. Again, coming from your equation sheet. This is the S bar matrix, all right? We know what S bar is. Again, we calculated it up here in part C, so we know what S bar is. We know what the values are that live in this particular entry. So what it's asking us to do is asking us to calculate eta xs and eta ys. All right, so it wants us to calculate eta xs, which is here, and eta ys, which is here. All right. So there's a couple ways that you can do this. Many ways that you can do this. Like, you know, the individual entries, you know, like the 1-3 entry here, you know, the 2-3 entry, you know, the 1-1 entry. So you could calculate EX, for instance, then use the 1-3 entry to calculate eta XS. Okay, fine. I mean, there's many different ways to go about this particular problem, but one clever way to do it is to look at the ratio between, let's say, this and this, right? So if you look at this and you say, all right, S bar 3-1 divided by S11, that's okay. This is the 3-1 entry. This is the 1-1 entry. So this is eta XS over EX divided by 1 on EX. All right. So in this case, you would get these EX terms like canceling, and this is just going to end up being eta XS, which is what you're looking for. So 3-1 divided by 1-1 is eta XS. Okay, so the 3-1 entry, we roll back up here, negative 0.0514. The 1-1 entry, 0.0571. So you can calculate this, punch this in, negative 0.901. So that's the answer for eta XS. You can do something similar for eta YS and understand that the S23 entry divided by the S21 entry is eta YS on EY. Sorry, that should be 22 entry divided by 1 on EY. That's what they are according to these equations. So we get, all right, the EYs will cancel each other, and you're just left with S23 on S22 is equal to eta YS, which is what you're looking for, right? So eta YS is S23 over S22. Let's look at S23. Negative 0.0441. Divided by S22. 0.07396. I'm going to say 0.074. And you'll end up with eta YS is negative 0.6. And that's that. Okay. So that's some clever manipulation of the entries of S to get you there. It's kind of nice. If the material were isotropic and we load in the same way, would there be shear coupling? No, the shear coupling coefficient only comes about because it's orthotropic. So the answer to F is no. No shear coupling. If isotropic. Okay. All shear coupling coefficients in isotropic materials are 0. There's quite a few notes about that in the lecture notes, so you can take a look at that. All right, that's problem numbers 4 and 5 for this week's study guide. So take a look at those, and we will chat on Thursday, which is tomorrow at 10 a.m. Okay? Talk to you then.